Problem 53 in 16.3, the question asks to find the average distance between points of the disk of radius A and the origin. So the disk filled in. So let me draw it. The disk is like this, supposed to be a circle that's filled in. R, remember, is the distance from the origin on the xy plane. And for this question, I'll actually tell you what the answer is, and let's see if it makes sense. The answer is 2 over 3a. So it says that the average distance from the origin in this disk is something like this. So this is 1/3, this is 2/3. This would be the average. And this does make sense. For example, it's larger than half because we have more points, more area that has distance from the origin greater than 1/2 of a. That's why it makes the average a little bit larger than 1/2. So this is the average, which is equal to 2/3 of a. Let's see if this is the correct answer. This is the formula from class. You need to integrate your in order to find average value of some function, you need to integrate this function over the region R and divide by the area of the region. Now, since we're integrating in polar coordinates, here will be your differential area, r dr d theta, and the integration is in terms of r in theta. In our particular case, since we're looking for average distance between points and the origin, this function f of interest would be r. Let's integrate f, so this would be the numerator. So we have integral over r of f, r dr d theta. Here I have this function. This is r dr d theta. Bounds on theta would be, well, we need to describe the full circle, right? So we're integrating from this theta equals 0, and then theta keeps increasing all the way until we make a full circle. This would make it theta equals 2 pi. And then r would go from 0 to a. So from the origin all the way to this guy. And then in the next step, I combined these two into r squared, and I separated the integral into two, everything corresponding to theta, and everything corresponding to r. I evaluated the first integral and got 2 pi. Then I evaluated the second integral and got r cubed over 3 from 0 to a. And this is equal to 2 pi over this 3 times a cubed, because 0 will just not contribute. Now let's find the denominator. Now, denominator is just the area of the circle, which is equal to pi a squared. But since finding this area involves polar coordinate integration, we might as well do it to get some practice. So this is the integral. We are just integrating once since we're just finding the area, and this is the differential area. Then we have, actually, I don't remember what notation text the lecture uses, so let's just remember this is differential area. So then bounds are the same as before, 0 to 2 pi, 0 to a, and here I get the same way separating the integrals, and I have 2 pi times, here since we have just r, we get r squared over 2. Sorry, this should be r. And then from 0 to a, and then 2 cancels, and we get pi a squared. And then we need to divide the two things together. So we have this one, 2 pi over 3a cubed, and pi a squared. Then pi cancels, a almost cancels, and we get 2 over 3 times a. So the answer was correct. Problem 23 from 16.3, you need to integrate 2xy, a function 2xy. It's a double integral over a region on the xy plane where x squared plus y squared is less than or equal to 9 and y is greater or equal to 0. This region is the same thing as saying that square root of x squared plus y squared is less than or equal to 3. Now, in this question, you can actually figure out that the answer is 0 because the region is like this. So we have distance from the origin, or r variable, is less than or equal to 3. This would be 3. And y is greater or equal to 0, which gives us this region. And you see that this region is symmetric with respect to the y-axis. So it's a mirror reflection with respect to this guy. So, and also 2xy is odd with respect to x. So whenever we're here, there is a corresponding point over here where the value of 2xy is going to have the opposite sign. And since the region of integration is symmetric, like this, we'll have integration over x is going to give us 0. But I'm pretty sure since it's in the polar coordinate integration section, I'm pretty sure you weren't meant to do it this way. I'm pretty sure you were supposed to actually evaluate. So let's do that as well. So in polar coordinates, we are integrating over dr d theta, but we need a scaling factor, which is the absolute value of Jacobian determinant, and in this case it's r. We have the integrand, which is 2xy. X is r cosine theta, y is r sine theta, and bounds on r and theta are like this. For theta, it's 0 to what? Let's see. We are integrating over this region. You see that this line corresponds to theta equals 0. And then we're integrating like this, and we go all the way to theta equals to pi. And then here r equals 0 to 3. So lines like this. Then the rest is just integration as usual. Here I split the integrals into 2. I have 0 to pi. Usually I pull out the constants, but in this case I kept it here. Then everything that has to do with r is in the second integral, which would be this, 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 and this. There's 3 r's, so this gives us r cubed. Now integration here, before integration, using double angle formula, you can rewrite this like sine of 2 theta, and then this integrates to negative cosine 2 theta over 2. Now, this, when you evaluate it at 0 and pi, you get 1 for both, right? Because cosine of 2 pi is the same as cosine of 0, which is 1. So then we have 1 minus 1, which cancels. So this is actually 0, so then we have 0 times something, so we don't even need to evaluate this integral, and we just get 0 as the answer, which is the same as we got here. Question 51 from 16.3, it asks you to use a double integral to find the area of the region inside two cardioids. One cardioid is this one, r equals 1 plus sine theta. The other cardioid is r equals 1 plus cosine theta. Let's sketch the two cardioids. The one in red on the r theta plane will look like this. It's going to be, going to have a value of 1 here, and then it goes like this, oops, and like this. So the graph will look like that. Then the graph of the blue cardioid is going to look like this. It will be 1 plus cosine theta. So it's like this, like this, like this, like this, like this, and like that. That will be how it looks. Let's find the intersection points. In our case, the intersection points are not too difficult to find because r is positive for both cardioids. So this means that there is only one way sort of for the two curves to intersect, because you know that things can get complicated if r can go negative, because they will not look like they're intersecting on the r theta plane. Since this point, it can also be that it's at negative r and theta shifted by pi radians, and it would look different, but it would actually be the same point. But then in this case, we don't need to worry about it since this r is just positive for both cardioids. Anyways, so we just need to figure out what this point is, this point, and this point. So then we'll have, but you can usually tell, once you draw it here, you'll immediately know if this is correct. So we want to figure out when it happens that 1 plus sine theta equals 1 plus cos theta. 1 cancels, so we need sine theta equals cos theta. Dividing by cos theta, we get that we want tan theta equals 1. This happens when theta equals to what? Well, it happens here and it happens here. So this would be theta equals to pi over 4. And so this would be here. It happens at theta equals to 1, 2, 3, 4, 5 pi over 4. This is right here. Between pi and 3 pi over 2. And it also happens at negative theta. So 1, 2, 3. So theta equals negative 3 pi over 4. Now let's sketch the two cardioids. We can use whichever one of 2 pi intervals to figure out the sketches. Let's say we use like this, from -3π/4, at which point, never mind, let's use from 0 to 2π. So at 0, the red one has r equals 1, then it becomes 2, then it becomes 1 again, and then it becomes 0. So we know it looks something maybe like this and like this. This is the overall shape, and then the blue one would be 2, 1, 0, 1, 2. So 2, 1, 0, 1, 2. And cardioids look in the shape of a heart. So we know it's something like this. Now, the reason I'm drawing it so slowly is because I want to make sure this intersection point is correct. So it looks like this here and like this here. Okay, and then the red one will look like that. And you see this intersection and this intersection. That's what we want. Okay, now what are we actually trying to find? We want the area inside both of these cardioids. That would be this area. Now, what does this correspond to? We could either try to sketch it out from 0 to 2π, but then we will actually end up having multiple regions. We'll end up having, you see, okay, I'll sketch it. So it's not the way we'll use it. So from 0 to π/4, it will be the red curve that determines where you end the integration, and then it becomes blue, and then it becomes red again. So this makes it 3 regions of interest, which will give you in the end 3 integrals. You can try it. That's probably what the most, like, how to say, default solution of this is. The faster way probably is to just go from -3π/4. So this would make it this one. So from here, you would go by the red curve up to π/4. So it's this one. Be careful, don't forget this small chunk. Up to π/4. Then from π/4 all the way to 5π/4, you would go by the blue curve. Then from 5π/4 until, oh, we're done. No, sorry. Okay, we just made the full circle because this angle and this angle is the same. This is the same point. Okay, so that's the region. Now let's set up the integral. Remember, areas when you're doing a double integral would just be integration of 1. So then we have this polar coordinate integration set up. We have dr d theta. Jacobian is equal to r for polar coordinates. For the first integral is the one that's up to the red curve. Let me actually draw it in red. So r here. Theta will go from -3π/4, this, to π/4. R will go from 0 to this red curve, which I forgot which one. It's r equals 1 plus sine theta. So 1 plus sine theta. For the second chunk, we'll have theta going from pi over 4 up to 5 pi over 4. And then r will go from 0 to 1 plus cosine theta. The next is integration. Integrating over r, we would get r squared over 2, and we evaluate at 0 and this endpoint, which gave me this. And then bounds stay the same, d theta, plus, same thing here, r squared over 2 is the antiderivative, and I plug in these numbers, I get 1 plus cos theta all squared over 2. In the next step, I expanded this out, and this 2 and this 2 came out of the integral. Then I have 1 plus 2 sine theta plus sine squared theta. Here I have 1 plus 2 cosine theta plus cosine squared theta. Next, what I did is I used double angle formula for this guy. So 1 minus cosine 2 theta over 2. And then the same thing for this one, cosine squared theta is 1 plus cosine 2 theta over 2. By the way, sorry, no, later, okay. So then, next is the antiderivatives. We have this guy and this guy combined gave me 3 over 2, and then I integrated, it became theta minus 2 cosine theta. The minus is because this is cos. Then we have this guy is gone, then we have this minus here, and then cos becomes sine when you integrate, and then 2 theta. This 2 was in the denominator, but because of this 2 it becomes a 4, and then the endpoints are the same, then plus 3 over 2 theta plus 2, well, 3 over 2 came from the same thing as before, from here and from here, 3 over 2 theta plus 2 sine theta. Because it's a sine, we put a plus, then it's plus sine 2 theta over 4 again. For the same reasoning, it was a 2, this 2 made it a 4, and we have plus here because of this plus. Remember here minus was because of this minus. Endpoints are pi over 4 and 5 pi over 4. Next, let's plug in the endpoints. Pi over 4 minus this guy is going to be pi. Remember, this distance from this point to, where is it? To this point is equal to pi. Well, basically it's this one and this one. Or you can just do the math and subtract them. So you have this. Then we have the following. Cosine of pi over 4 is equal to, oops, wrong color. Cosine of pi over 4 is equal to root 2 over 2. Cosine of negative 3 pi over 4 is equal to, well, it's a negative number, so it's negative root 2 over 2. Since we're subtracting them, we end up with just double of the first one. of this first upper endpoint. So then instead of 2, we get 4, and then root 2 over 2. Then we have minus sine of, well, this makes it pi over 2. This is 1. And then minus sine of negative 3 pi over, instead of 4, we have a 2. This would be this 1, 2, 3 pi over 2. Since minus, we go clockwise. This is also going to be 1. So this is 1. So we have 1 minus 1 over 4. And then we have plus 1/2. This again is pi, if you subtract these two things, minus, okay, let me explain this one. Sine of 5 pi over 4 is equal to, it's a negative number, so it's negative root 2 over 2. Sine of pi over 4 is root 2 over 2, but we're subtracting. So we end up with double of this guy. So negative 4 times root 2 over 2 instead of 2 times root 2 over 2. Then we have plus sine of 5 pi over 4 is, sorry, of 5 pi over 2, because of this 2, is equal to, so 5 pi over 2 is the same thing as 2.5 pi. So this whole thing is the same as sine of 0.5 pi, which is 1. So then we have 1 here, and then at pi over 4, we'll end up with sine of pi over 2. So we have 1 again. Okay, now we have, this is the same, this becomes 2, root 2. This guy cancels, because 1 minus 1 is 0. Here, same thing, minus, this is 2, and this cancels. So then we have 3 pi over 2 minus 2 root 2. Same thing here. This is equal to, let's see, this one and this one are the same, so we can just remove the 1/2. So we end up with 3 over 2 pi minus 2 root 2. Now I just wanted to, well, this is the answer, that's what we're looking for, but I just wanted to point out that this guy and this guy ended up the same. The reason why geometrically is because, you see, this integration was everywhere where the red curve was basically like determining things. So it's from negative 3 pi over 4 to pi over 4, this one. And then the rest is the second integral. So this means that you see how they're the same? That's why we have it the same number here and here. In class, you've covered several very standard coordinate systems. It was Cartesian and integration in Cartesian coordinates, integration in cylindrical coordinates, and integration in spherical coordinates. So that's really common 3 ways to integrate in 3 dimensions. Now I'm going to show you how to find volume of a cone using each of those 3 different coordinate systems. But before we do that, let's sketch these equations, which all turned out to be cones. So for this one, what this guy is saying is that z divided by the distance from the z-axis is equal to a constant k. Or in other words, z equals to some constant times distance from the z-axis. So this describes a cone. And the ratio of height to the radius of the cone, height over radius, is given by k. Now the reason I didn't draw the bottom part of the cone is because this has a square root and it's a positive number. So z is positive. So this describes surface of the cone. This is the same, so this is the cylindrical description of the exact same cone because r is equal to square root of x squared plus y squared. Now here we are saying that phi equals to some constant, so this is the spherical description, spherical coordinate description. And this also describes a cone where the angle between the cone and the z-axis is equal to phi naught. Now let's do the actual problem. So the problem is to find the volume of a cone with height h and radius r. And the cone is going to be oriented in this way. In Cartesian coordinates, it doesn't really matter too much, but then, for example, for spherical coordinates, this description does make it, I think it should make it a bit simpler to integrate. Okay, and I'll tell you right away the answer is this. This you can look up as a formula for the volume of a cone, pi r squared h over 3. So let's see whether by integrating in these three different coordinate systems we'll get the same result. Let's start with Cartesian coordinate integration. The order that I chose is dy, dx, dz. You can choose a lot of different other orders, but that's the one we'll do today. So I'm going to use explanation the way it's in the textbook to figure out the bounds on y, x, and z, because I just checked it today. I think it's pretty clear. So, okay, so on the innermost integral, we would want the bounds to be the surfaces that bound this sort of last integration. You know, the one where we integrate over y? So you see, you are going to integrate from the back of this cone to the front of this cone. And by back, I mean negative y part, and by front, I mean the positive y part of it. So let me make this upper bound red. This would be this surface, the front of the cone. And then the back of the cone, I'm going to make it blue. This is the lower bound on y. It would be right here. So this would be here. Now the bounds on x and z would need to describe the projection of this entire volume onto the xz plane. And I'm going to actually draw the xz plane here separately as well, so you see what's happening. So this would be x, and this would be z. So you see that this sort of, we can think of it as shadow of the cone, or we could think, but since it's right, accepting xz plane is kind of hard to imagine it being a shadow. It's more like a projection of the cone onto the xz plane. So it's sort of like you squished the cone onto this plane. So it's this triangle, like this. Now we just need to figure out what the bounds would look like for a triangle like this. This triangle has here it would be at negative r, here would be at r, and here it would be at h. The bounds on z are outermost, so we're going to have 0 to h. And then for x, we need to describe this guy and this guy. Well, we know that equation of this would be, well, here we'll have x equals to r over h times z. And this one is going to be same thing but negative. So x equals negative r over h z. So negative rz over h to rz over h. For this blue bound and red bound, we will have this. We will have the actual surface of the cone. Remember how surface of a cone was described by z equals to k times square root of x squared plus y squared? Or in other words, z squared divided by k squared equals to x squared plus y squared, or y squared equals to z squared over k squared minus x squared, but we haven't said what k is. K is the ratio of height to the radius. So we have z squared divided by height squared, and then here we'll have radius squared, and then minus x squared. So the bounds, right, and then y, when you solve for y, you will get that y equals plus or minus square root of that. So r squared, z squared over h squared minus x squared. Now the plus would be the red surface, and the minus would be the blue surface. So here we'll have minus square root of r squared z squared over h squared minus x squared. On the top we'll have plus square root of r squared z squared over h squared minus x squared. Now let's just integrate. So the integration over y is going to just give us this minus that, and since these two things are the same except for the sign, we get 2 times square root of all this stuff, and again dx dz, these bounds are the same as before. Now a convenient thing to do is to use trig substitution. So x equals to well, square root of this guy times sine of some angle. Let me sketch this. This is the way I like to think about it is like this. So I imagine that this is x, then, and this is alpha, and this guy is rz over h. Then x equals to rz over h sine alpha. We also will have that this guy is this squared minus x squared, all of this square rooted, which is exactly this side. And we know that this side geometrically is equal to rz over h times cosine alpha. And this is true whether alpha is positive or if alpha is negative. Because if alpha is negative, then x becomes negative, but that's okay. We'll just have this situation. and x is less than 0 for this one. Then dx is rz cosine alpha d alpha. By the way, you don't have to draw this picture or anything. If you like any other way to do trig substitution, you can use that. Okay. Now the bounds on the integral are negative rz over h and rz over h. So negative rz over h happens when what happens? So when alpha increases, this side stays the same. So what we're describing is a circle like this. So if alpha is all the way here, then x equals to rz over h. This is this case. Alpha equals pi over 2. For x to be negative rz over h, we need alpha to be negative pi over 2. So, okay, let me show this. This would be kind of like x-axis. And this, well, it's y-axis, but it's not like this axis. It's just like, I'm just using this picture to do the trig substitution. Anyways, so now we have the following. So the outside integral 0h dz, that all stays 0h and dz. On the inside, we have, instead of this and this, we have negative pi over 2 and pi over 2. 2 stays. Then we have this guy, which we figured out, oops, no, wrong one, was this. Then we have dx, which is this. So rz over h cosine alpha d alpha. The next thing that happens is this r over h and r over h come out of the integral because they're constants. The integration over z, let me highlight it. Integration over z is this 0 to h z squared dz. And then what we're left with is integration over theta. So it's this, sorry, not theta, alpha, this, and I also didn't take this out of the integral, so there is that as well. So that's where I got all of this, and then the green part is this guy. And that was the constant. Next thing I did is I integrated over z. This gave me z cubed over 3, and plugging in h, I got, well, h and 0, I got h cubed over 3. For this guy, I used double angle formula to rewrite this as 1 plus cosine of 2 alpha. And when I integrated that, I got alpha plus sine of 2 alpha over 2, from negative pi over 2 to pi over 2. Then I rewrote this, well, I canceled h. You see, this is the same thing as r squared h squared. And this guy partially cancels with this. So then I have r squared h over 3, and then this guy. Now this one will give me pi over 2 minus negative pi over 2, so pi. And this one, when I plug in pi over 2, I get sine of pi, which is 0. And then for this guy, we get sine of negative pi, which is also 0. So this part goes away. Now we have r squared h over 3 times pi. And just a reminder, the answer was pi r squared h over 3, which is the same as this one. So this is correct. Now, I don't know if this threw you off or not. You see how this is a double integral, but I'm only doing a substitution with x. So I'm not doing any of the Jacobian stuff here. So like my, yeah. So the reason it's okay to do this is because we're treating z as a constant, and we're not transforming z in any way. It's just x that's being transformed. So if we're treating z as a constant, we can just do this substitution like this. Now you can, if you want, do a substitution, think of it as a substitution of two variables. It would involve, well, the same trig substitution as we did, and then instead of z, there would be just no substitution, just z stays as is, we don't need to transform it. I guess we'll rewrite this one as r v over h times sine u. So then x and z become something in terms of v and u and just v. I'm not going to show you the details because I actually haven't tried, but I'm pretty sure you'll get something equivalent. Calculations should end up very similar, and you'll get the same answer. Now let's do cylindrical coordinate integration. For this one, I wrote it in the order dz, dr, d theta. So the bounds on z are these final bounds that you get that you need when you're integrating over vertical lines like this. So the bound would be the surface of the cone, the lower bound. Let me make it blue, it's this one. It's the surface of the cone. The upper bound would be this surface. And now the bounds on r and theta are such that are basically going to describe the region on the xy plane that you get when you sort of squish this cylinder, this cone onto the xy plane. So if you squash it, you'll get a circle of radius r. So your bounds on r and theta are just going to describe this circle. So it's this, and then the radius is, whoops, r. So let's write what the bounds are. So in the end, the bounds on theta are going to be 0 to 2 pi because we're describing the full circle. The bounds on r are going to be from 0 to r to capital R, and the bounds on z are going to be from this one, z equals to k root x, well, sorry, we're doing cylindrical, so kr, where k is the ratio of height to radius. So this is h r over capital R, and then the upper bound is just h. The red one is z equals h. Now, we are just integrating one, but we need to always remember that in cylindrical coordinates, we need a Jacobian. Jacobian is equal to r, and then we just need to integrate. For theta, nothing depends on theta, so I pulled everything out and I got this. The rest is 0 to r, hr over r to h, r dz dr equals to integrating over. I have a gigantic fly in my room. I don't know if you can hear it, but it's really loud. Sorry. Okay. So this is 2 pi. And this one, well, r is just a constant as far as z is concerned. So we get r times h minus hr over r. Then this, when I expand, I get hr minus hr squared over r. And then dr stays. This is equal to 2 pi, and then we get the following. When we integrate this guy, we get hr squared over 2 minus hr cubed over r from 0 to r. And this one, when we plug everything in, we get h capital R squared over 2 minus hr cubed over r. Then we cancel this and this partially, so this becomes a 2, and this goes away. If we factor out hr squared, we're left with 1/2 minus 1/3, and this is equal to 2 pi hr squared, and then this guy is equal to 3 minus 2 over 6, so 1 over 6. That's how I got this 6 here. Then I cancel this partially, and I get this, and remember, this is the same thing as we had before, pi hr squared over 3. So this is correct. Let's integrate in spherical coordinates. Here, the order I chose is d rho, d phi, d theta, which is pretty standard. Here we have the following. With d rho, you know that this is the innermost integration, and by the time you get here, you have phi and theta are fixed, and what you have is integration over lines that go outward from the origin, and rho is increasing all the way until it hits this surface, and then it stops there. So you go this way until you hit that surface. So we need to just figure out where this stops and where it begins. Well, it begins at rho equals 0. That one's easy. And we need to figure out where it stops. So this one, in Cartesian coordinates, it's z equals h. But that's not in terms of rho, phi, and theta yet. If we write it in terms of spherical coordinate variables, we'll get rho cosine phi equals h. Since we need the bound on rho, we would write it as rho equals h secant phi. So I divided by h, by cosine phi. So this would be h secant phi. This is this surface. Now we need bounds on phi and theta. For theta, we know that we need to describe the entire way around the z-axis. So this would go from 0 to 2 pi. For phi, we need to describe from this angle all the way to this angle. Let's find what it is. So this beginning is at 0 and the end is at what? We know that if we look at this triangle, let me make it different color. Let me make it cyan. If we look at this triangle, we see that its height is h, and this is r, and this is 90 degrees, and this angle is the one we need. And we know that this angle then is inverse tangent of r over h, so opposite over adjacent. So those are the bounds, and now the Jacobian is rho squared sine phi. Then the next thing that happens, we have integration over theta. Here nothing depends on theta, so I got this integration 0 to 2 pi d theta. Everything else stays the same. Then this integration gives us 2 pi, this, and then integration over rho gave me this. So sine phi stayed the same, but now we have rho cubed over 3 from 0 to h secant phi. This gave me h secant phi, all of that cubed over 3, and sine phi stayed the same. Everything else didn't change. Next thing I did is I took this h and I cubed it and I pulled it out of the integral. So I have this h cubed. I did the same thing with 3 except without the cube. This is here, this was the h. I also rewrote secant cubed as cosine to the negative 3. The reason why is because I'm hoping to use the chain rule because derivative of cosine is negative sine. So that's what I did. Now the antiderivative of this guy is this. So we know that it needs to be cosine to the negative 2 phi over negative 2, but we need to be careful if you differentiate this. Oh, sorry. This is antiderivative. If you differentiate this, you are going to get also negative sine phi. So sine phi is fine, but then the negative is not. So we need to put a negative here. So now we have negative cosine to the negative 2 phi over negative 2. And then these negatives cancel. And then points are 0, tan inverse r over h, okay. Next thing that happens is this cancels. We have pi h cubed over 3. I wrote cosine squared in the denominator. Then I evaluated at the endpoints 1 over cosine of that crazy thing minus 1 over cosine of 0. Cosine of 0 is 1. That's what I wrote here. Now for cosine squared of this guy, here's what we have. We know that tan inverse of r over h is this phi naught that we were looking for right here. So this largest angle here. Now cosine of phi naught, or cosine of tan inverse r over h, is given by using this cyan triangle. It's going to be h, the adjacent, over hypotenuse. So h over h squared plus r squared all square rooted. But we don't have just cosine, we have cosine squared. So we need to square this guy, and we will get h squared over h squared plus r squared. So then I brought this into the numerator, got h squared plus r squared. In the next step, I multiplied, I brought this to be to have the common denominator which is h squared, so it's h squared plus r squared minus h squared. Then I canceled this. I also partially canceled this, so I got pi h over 3 r squared, which is the same answer as we had for the other two coordinate systems. Now for this particular problem, it's up to you what you like better. I personally like cylindrical. It seems to be the shortest, and it doesn't involve as many as many changes of variable or anything. So I'd say this is the most convenient. But sometimes you'll be told which coordinate system to use, so you do need to know all of them, even if you have a preference. Question 65 in 16.5, you are given an integral of some arbitrary function of rho, phi, and theta. This is, of course, spherical coordinate integration. You have the Jacobian already written, rho squared sine phi. The order is d rho, d phi, d theta. And you have the bounds given here. And you're asked to write the iterated integral in the orders d rho, d theta, d phi, and d theta, d rho, d phi. So let's do this. But first, let's sketch this region. Oh, by the way, I think you were told to actually sketch it. This was part of the task. In either case, I think it's always a good idea, almost always a good idea to sketch it. Let's start with drawing the bounding surfaces. I'm going to start with the inner surfaces. Let's start with this one. Rho equals 2. This is a sphere of radius 2. I'm going to draw that. This is a sphere. I'm going to actually in parallel draw a ZY trace of this whole situation. This is Z, this is Y, okay? And we've determined that we have a sphere. Now we have, right, and it's 2 here, 2, -2, and -2. This is rho equals to cosecant phi, which is the same thing as writing rho sine phi equals 1. What I did is I multiplied both sides by sine phi, which made it 1 on the right-hand side and rho sine phi on the left-hand side. This is saying that the distance from the z-axis is equal to 1, which is the same thing as saying cylinder of radius 1. So this would be surface like this. And then here it's like this. Let me draw it better. Okay, like this at 1, and then we have this guy at -1. Next, we want to get these ones. The upper bound is pi over 2, phi equals pi over 2, which is the same thing as saying xy plane. So this would be that. And then here it will look like this. We have the lower bound on phi equal to pi over 6. This describes a cone. Now we want to understand where exactly this cone will go. For this, here's what I'm going to do. I'm going to try to understand what this angle is. I'm going to first solve for this angle. Now this angle is equal to inverse, I'm going to use sine, so this, remember, was 1, so this is inverse sine of 1 over hypotenuse. Hypotenuse is 2, since we're talking about sphere of radius 2. This is equal to pi over 6, because remember, sine of pi over 6 is equal to 1/2. So this means that this is actually pi over 6 and this is good news because it makes the shape slightly simpler to draw, because this wonderful cone will pass exactly through this point. And this one, same thing here. And here it will look like this. So now, oh, right, and then the bounds on theta are 0 to 2 pi, which makes it a full circle. This is, well, if it weren't 0 to 2 pi, we would need to draw two more surfaces that are bounding the shape. But in this case, 0 to 2 pi just means all the way around z-axis. Or you could think two surfaces co-located with xz plane. It's kind of like you have a cake. This guy is it's kind of like this. If you have a cake, basically it's cutting out, oh god, this looks horrendous. It's cutting out a chunk of a cake. But because it's going all the way from 0 to 2 pi, you end up just taking the whole cake. So you don't need to worry about these guys. Okay, so now to get the shape, we can technically just go ahead and fill in whatever is in between all these surfaces. But I like to do a sanity check. I like to think about how this integration goes. We could start with the inner integral. For example, you don't have to start from the inner integral, but that's an option. Integration over rho gives you rays that go that have already, so by this time phi and theta are fixed. So here you're integrating over rays going away from the origin for fixed phi and theta. Each of those rays would go from the blue to red. So here is not included, here is included, and here is not included. So rays are like this, and then same idea on this side. Next we have integration over phi, so which goes from pi over 6 to pi over 2. This means that these rays will happen from the ray that aligns with this cone all the way to pi over 2, all the way until it hits the xy plane. The same thing happens here. I'm only showing you the YZ trace because it will get really messy on this drawing if I try doing it. But just imagine I'm doing this for every possible theta value. So then next thing that happens is this. We're saying that this situation happens all the way around. Sorry, I haven't explained this, have I? Okay, so here what we have is that no, I think I did explain it. Okay. So basically, this is just saying that this situation, which I drew for theta equals 0, and also for theta equals to pi, because this is the negative y, negative y, z, I guess negative y and z plane, part of the plane, is going to happen not just for these values, but for every single value of theta. So then we need to imagine taking this guy and revolving it around to form the solid. So this will make it like this. You will have this ring here. This is not aligned with the surface of the sphere, so it's a ring, it's flat. And then you have this guy, like this. Well, I said flat, but it's more like it's just missing. There's nothing there. So it's more like a hole. Then you have this, then it's bounded by the xy plane. So this is a hemisphere that goes like this. So it's kind of like a sphere, but you have a hole extruded from it, and the hole has a shape of a cylinder. Now let's figure out the description in terms of d rho, d phi, d theta, and d phi. For phi, we will here we'll have d rho going in the same kind of rays, so we can write cosecant phi to 2, so it's from this blue to the red. This describes the rays I was talking about. The rays happen all the way around the circle, so this would be 0 to 2 pi. And the angles phi for which the rays happen go from pi over 6 to pi over 2. So it's the same bounds as before. Now let's do the order d theta, d rho, d phi. Here I've redrawn the shape of the solid and also the YZ trace for the half corresponding to theta equals 0. So on the inner bound we have d theta, and the integration is happening for fixed rho and phi. So fixed rho and phi on the YZ trace, for example, correspond to just a point. And then by varying theta, we would describe a circle around the z-axis, like this. And then what are the bounds on theta? Well, those are just 0 to 2 pi. And then we want to integrate for every one of those, we want to have those circles happen for different values of rho. And what are those values of rho? Well, for fixed angle theta, values of rho that we care about would go between the blue line and the red line. And you see how I'm drawing it on this cone? So that's because phi is fixed. So then these bounds would go between the blue line cosecant phi to rho equals 2. And then each of those lines should happen for different values of phi. And what are the bounds on phi? Well, those go between the cyan line and the green line. So this would be pi over 6 to pi over 2. Now you may, you probably know already that when you're changing order of integration, you can't simply swap the bounds on the integral. But in this case, you may notice that actually you just swap the bounds on the integral. So theta bound just became on the inside instead of this one. The reason it's possible is because the bounds of integration are still compatible with this new order. So in this particular case, it doesn't always happen. In this particular case, we have that the bounds on rho depend on phi only, which is allowed. So this is fine. So we don't have any involvement of theta in these bounds, so that's fine. And the outside bounds are just constants. And then the inner bounds are also constants, which is also fine. Now, if the order was had rho on the very outside, then we couldn't just write cosine phi to 2 on the outside, because that's only allowed for inner integrals.
Problem 81 from 16.5, you are asked to find the volume common to two spheres. The first sphere is at the origin and has radius r. The second sphere is shifted up by a and has radius a, and you're also told that a is greater than r over 2. Let me sketch a YZ trace of the situation. And let me also sketch a full 3D drawing. So YZ trace, we have one sphere of radius r. The second sphere is shifted up by a, and we know that, so basically it will go from z equals to a minus the radius of the sphere, and then a plus the radius of the sphere. And we know that this upper z is going to be greater than r because of this. If you multiply both sides by 2, you'll get that 2a is greater than r. So then the sphere will go from this height up to somewhere above the end of this sphere. We don't know where exactly, we don't know what the size exactly is, but we at least know it's not going to end here. So it's not this situation. It's more like this. And the center of this sphere is this, and then this is the radius. The full 3D drawing would look something like this. We have sphere 1 at the origin of radius r, and then the second sphere goes something like this. And we also know that there is these two intersect in a line. Well, in a contour, which is a circle. On the YZ trace, it's going to look like just two dots. So let's see. And what we're trying to find is the volume that I'm going to show in gray. So it's this volume. Like this, and like this. And then if you look on the trace, so sort of a cross section of this situation, what we're looking for is this. Now, I want to find this volume using spherical coordinates. For this, I will need equations of these two spheres in spherical coordinates. Now, for the sphere number 1, it's pretty obvious. It's just rho equals r. Equation for the second sphere, though, is more complicated. Let me label this and this. For the second sphere, what we have is rho equals 2a cosine phi. Let me explain why. The second sphere is given by x squared plus y squared plus z minus a squared equals to radius of the sphere squared. This a is because the sphere is shifted up by a. If I expand this, I get x squared plus y squared plus z squared minus 2az plus a squared equals to a squared. A squared cancels, so we get this is rho squared minus 2a rho cosine phi, because z equals to rho cosine phi, equals 0. Now, because we don't really need to worry about rho equals 0, since rho equals 0 is just one point at the origin, we can write rho equals to, basically we can cancel this rho. This is equal to cosine phi, and then I'm just going to write don't worry about rho equals 0 case. Okay, so let me label everything. This sphere, well, this is the trace of it, and this is the 3D picture. This would be rho equals r, and this would be rho equals to 2a cosine phi. Now, what I'll do is, I'll need to figure out where this intersection happens. You'll see why I'll need this information in a minute, but let me just find it first, and then you'll see where I'm using it. So for now, just if you have a question why I'm doing this, just hold that thought. Okay, so I want to find what this red line is. The red line happens when this row, where basically it happens for the value of phi, where rho equals to r. Because if rho, basically if the two spheres intersect, it means they have the same value of phi and the same value of rho. Now, well, assuming, we have, how to say, okay, I'm not sure if it's the case anymore. Okay, you know what? I'll have to think about that. Anyways, but you know that if we go somewhere here, for example, where we're not on the intersection, you know that rho at this point is greater than r. The only points where rho is equal to r, if they are on this sphere, are the ones that are also on this sphere. So we need that this guy equals to r. That's what I wrote here. So then I wrote r equals 2a cosine phi. Next, I solve for phi. So I divide both sides by 2a. So then this cancels. And then we have phi equals to cosine inverse of r over 2a. So I took cosine inverse of both sides and I got this. Now, the reason I'm writing this guy is because just by itself, this will describe a cone. But we know that the set at which the two spheres intersect is not a cone. It's a circle. So I need some more information. So I'm saying that rho equals r at the intersection curve. Now you'll think, well, I had intersection of two things, and now I'm giving you the answer as intersection of two things. But you should realize that intersection of two spheres is a lot more complicated than intersection of a cone with this constant phi and a sphere with constant rho. So then the next step is to figure out how to integrate this. And this is where I'll use this intersection contour that I just found. What I'm going to do is I'm going to integrate with rho being on the innermost integral. In this way, I have two regions of interest. The first region of interest is the one where I'm integrating up to rho equals r, and the second region of interest is where I'm integrating up to this function. So I'm going to highlight them in different colors. I'm going to use blue for this guy. Now, you should remember that this is a trace. This is not the actual shape. I can try to show you the actual 3D shape, but it's going to be messy. You know what? I'm not going to do it. But just imagine this revolved around the z-axis. You're going to get this kind of like an ice cream cone shaped shape. Now, the second region of interest is going to be the green one, this region. Let me start with the blue region. The blue region will have the bounds on rho going from 0 to r. The bounds on phi are going to be from 0 up to this phi. Now, this is why I found where the curves intersect. I need to know what this phi is. So this phi would be cosine inverse r over 2a. And then bounds on theta are just 0 to 2 pi. For the green region, it's a little bit more complicated. Before I can write out the green region, I need to actually understand what happens to phi here, because it's not very obvious if, how to say, where exactly phi needs to end here. So I'm going to draw this guy with rho versus phi so that it's easier to picture, and I'll try to convince you that the bounds should be from this phi to pi over 2.
Let me show you. So if I sketch this, rho versus phi, I'm going to start at 2a, and then I'm going to, at pi over 2, I'm going to get to 0. And then rho will become negative, and then positive again. So we don't actually want this whole chunk. We only want to integrate the part that's, how to say, we only want to consider this sphere as being due to this part. So you see how when phi equals 0, that's when you're looking at being aligned with the z-axis, you have this rho, distance from the origin, is equal to 2a. Then when you increase your phi, rho starts becoming smaller and smaller until eventually, when you are getting at angles closer and closer to pi over 2, your distance from the origin becomes closer and closer to 0. So you see how going up to pi over 2 is what you need to get to sort of describe this entire sphere. Now you shouldn't go any further because you've already described the whole surface of the sphere with this, just with the interval 0 to pi over 2. And if you go further, you're probably going to double count something. Okay, so I hope I've convinced you that this green part is going to go between this and pi over 2. So this is going to be cosine inverse r over 2a to pi over 2. Oh, and I actually haven't described these bounds yet. So bounds on rho are going to be from 0 to the surface of this sphere, 2a cosine phi. And bounds on theta are 0 to 2 pi. I'm not going to integrate this, but I just wanted to show you how to set it up because I figured it's a rather difficult question. So I wanted to show you. It's not the only way to do it. There's, yeah, a whole bunch of other ways.